حياكم الله جميعا في اليوم الثاني من برنامج معسكر أرشفة، والمقدم بالتعاون بين فريق أرشفة والتمييز الطلابي. نوه الحضور بأنه اليوم سيتم مراجعة فاينل إكزام والمقرر إن شاء الله يوم 28 ديسمبر. أذكركم بزيارة قناتنا على اليوتيوب، في عدد من الشروحات لا بأس بها للمواد الفريشمان بشكل عام والفيزيكس 1 و 2 أيضا. أترك المجال للدكتور عادل ليبدأ الحصة. حياكم الله.
السلام عليكم. بسم الله الرحمن الرحيم. So today we'll do physics 102. It's not 101, so it's 102. Final exam preparation session. Okay, so for this I chose some problems from the old exams and some problems from the book. I tried to keep the problems not very difficult and not easy. Okay, so it will give you a flavor of what will you have in the exam. Okay, let's start. Okay, so for the first one, I chose the problems randomly. Let's go to the number one. Number one is here. Okay, so for this one, we have a sinusoidal wave moving along a string, which is shown here. It's shown twice, so this one and this one at another time. A crest A travels in the positive direction of an x-axis by distance d equal to 6 centimeter. So first thing you need to keep in mind is that here it's in centimeter, not the international unit. So it travels 6 centimeter in 4 milliseconds. So it goes, let's say, from this shape to this shape and travels a distance from a crest to another crest. Crest يعني القمة. Crest هي القمة. So it goes from a crest to another crest in 4 milliseconds. And the distance d is given, 6 centimeter. The tick marks is this one. هذه العلامة هون. Tick marks along the axis are separated by 10 centimeter. So this one is 10 centimeter, this one is 10, 10, and so on. The height h here is 6 millimeter. If the wave equation is of the form y of x and t equal to ym sine function kx plus or minus omega t, what are ym, k, omega, and the correct choice of the sine of omega? So here, if you can answer this one, you can answer all the questions related to this chapter. Great. So the starting point, we have here h. H is the distance from here to here. So from the minimum here to the maximum here. So we know that ym, which is the amplitude is h over 2, which is ym. So ym is this. H is given in 6 millimeter over 2, and this will give 3 millimeter. I can keep it in millimeter, but I keep in mind that it is in millimeter. Great. So this is the amplitude. Amplitude should be always positive. We put the amplitude when we talk about the amplitude, it is positive. So this is the first answer. The second answer, we need to get the velocity or the speed of the wave. So v is equal. Here, since the wave is traveling a distance d in a time t, so we say that it's just d over t. D over t. The distance over the time, and this is 6 centimeter. I need to work in the international units over 4 milliseconds. So I put it here in the international units, and this should give me something like 15 meter per second. So this is 15 meter per second, and this is v. I always work in the international unit, so the final result is in the international unit. Great. What can we get also? Let's put 3 here. We need k. Okay, so we got the amplitude. Now we need the wave number k. Okay. So K, by definition, we have a definition for K is 2 pi over lambda. So K is 2 pi over lambda. What is the definition of lambda? Lambda, we need to take any point, let's say this one, and go to the same point in the same direction until here. Not this one. It's until here because we need to go in the same direction. So here we are going up, here we are going up. So all this distance will make lambda. So this one is by definition lambda. So lambda from the figure here is we have 1, 2, 3, 4 tick marks, and each tick mark is 10 centimeter. So it's 4 times 10 centimeter, which is 40 centimeter and 0.4 meter. In the international unit, it's 0.4 meter. Now I come back. Oh, let me do it here. You can stop me at any time, please. You can ask questions, please. Okay.
دكتور.
Yes, تفضل.
معليش بس المسافة اللي الأخيرة عند النقطة الأخيرة كيف صارت 10؟ هي أقل من 10.
هذه المسافة هون؟
معليش لو تقرب بس عند النقطة الحمراء الأخيرة. إيه هو المسافة بين النقاط المتقاطعة والخط المتصل 10 سنتيمتر صحيح؟
المسافة شوف هون تيك ماركس، هذه هي التيك ماركس، العلامة هون. هذه هون 20 هون 30 هون 4 صح؟
تمام. كنت أحسب النقاط الغير متصلة. يعطيك الله.
لا we work with هذه القطعة المتصل، الخط المتصل. Okay. So it is given here. It's 10 centimeter for the tick mark, and هون you see it is passing through the tick mark exactly. So it's 4 times 10 centimeter. It's 0.4 meter. شكرا على السؤال. So here, so K is equal to, I come back here and continue, is 2 pi over 0.4. Okay, and this, if I check my numbers here, it is giving me 16 rad per second. Okay, so this is the result. Great, so we had now Ym, amplitude, velocity, and the wave number K. We want the angular frequency now, omega. Omega, by definition, it's K multiplied by V. So it is 16, V is 15. I am in the international unit, both of them. So here it will give me 2.410 exponent 2 rad per second. The unit of the omega is rad per second. So I have almost everything. Now I can write what is the correct choice of the sign in front of omega. So y is equal to ym cos sine kx minus omega t. Here I choose the sign minus. Why I choose the sign minus?
Because the W is
right.
Yes, because it is going to the right. Okay, so I will make a comment on this right now. So ym is 3 millimeter. I can put it in 3 millimeter, no problem for ym. If I put it in 3 millimeter, the result also will be in millimeter, no problem. So I keep it 3 sine k is equal to 16 x minus 2.4 10 to the power 2 t. Great. Okay, now about the sign. I'll just make a small comment about the sign. What if they told us that the function is something like this? I'll put it in another color. Sine minus k x plus or minus omega t. So what do you think?
It's correct because it will be the different sign.
No,
When we
no,
have
I mean,
different sign,
what's the sign here? It will be plus or
Left
minus.
side. Left side.
plus.
Yes.
Yeah,
So I
should
will
be
just
different.
remind you. Yeah, I will remind you the rule. So you see, in the first one, I will write it in red. I can write it sine k and x minus omega over k t. So it's x minus v multiplied by t. If you have something like this, x minus velocity time, this one is going to the right. Okay. Now here, the second one, sine. Here I need to take minus k as a factor. I will have here x, and I need to have omega to have a wave function going to the right. Okay. The rule says that you need to see here x minus vt. Minus vt. If you see x plus vt, it will be. So you need to take either k or either minus k, depending on what you have here. Okay. So the important is what is in brackets inside here, x minus or x plus. Is it clear or a little bit confusing? So down here, if you can write your function as minus vt, right? If you have f plus vt to the left, okay? So this one to the left, this one to the right. So in order to express this, you need to take the factor of x. You need to take the factor of x outside, so that at the end you will have this. Or okay, if you have no question, I will go to the second problem.
Doctor, I have another way, but I try it. It's not working. I don't know why. If we can we solve the wavelength in another way? Like we can say the period takes 6 centimeter. It's 4 milliseconds, and if we multiply it by 4, it will give us 1 period.
Yeah, be careful. The 6 centimeter here, you do not know it represents what. Here the points are not passing exactly through the tick marks, so you cannot use the 6 centimeter here to get the wavelength directly. You cannot.
But I think they are vertical. They are vertical at the same point.
No. The be careful. The 6 centimeter. You see here the wavelength is 40 centimeter, and 6 it does not divide 40, so it's not. Cannot pass exactly through those points. We can discuss this.
I'm
Yes?
sorry, Doctor, but I don't mean the 6 for the H. I mean for D.
For D here, what was the D here? Yes, it's 6 also for D. 6 centimeter. I was talking about this one. 6 centimeter here. D is 6 centimeter. Or 6 is it? Yeah, 6 centimeter. Okay. Please. I can discuss with you at the end of the session. Is it fine for you?
Okay, it's okay.
Great. Thank you. Okay, let me go to the next problem. So this one, in this problem here, it's a typical problem for interference. If you understand this, you will understand most of the problems concerning this chapter. So here we have sound with 40 centimeter wavelength, travels rightward from a source. So here we have a source, and through a tube that consists of a straight portion. We have a straight portion like this, and a half circle. Okay, part of the sound wave will travel through the half circle and then rejoins the rest of the wave, which goes directly through the straight portion. This rejoining results in interference. What is the smallest radius r that results in intensity minimum at the detector? Great. So to solve this problem, we have a wave. It goes like this. Then part of the wave will continue directly straightforward like this, and the second part of the wave will go. Probably this one is not good. I will use the it will use this. It will follow this this path like this in blue. Okay. So here at the detector we will have two waves. Okay. We will detect the interference of two waves. Great. First of all, we need to look at two things. It's either delta D, either delta phi. So this one is the difference between the two paths. This one is the difference between the two phases. If we look at this, we will have an interference constructive if delta D is equal to n times lambda. Okay, n times lambda, and destructive if delta D is equal to 2n plus 1, or sorry, yes, 2n plus 1 lambda over 2. Okay, so here it's half the wavelength. Half the wavelength. So this one is for delta D. Here constructive interference, here destructive interference. Here we'll have maximum of amplitude, here we'll have minimum of amplitude. The same way, if someone else is working with the phase, constructive if delta phi is equal to n times pi, or 2 pi, sorry, 2 pi n times 2 pi, and destructive if delta phi is equal to 2n plus 1 multiplied by pi. Okay, so this is the difference. The two ways are correct. It's either delta D or delta phi, the phase or the difference of the path. Great. Let's look at here. What's delta D here? Delta D, one is taking this length, the other is taking this way. The difference between the two distances is equal to, here they are the same distance, here the same distance. So it's only here. One has pi multiplied by r, and the second is minus. This distance here is twice r. So this is the difference of distance between the two paths. Okay? This is the difference of distance between the two paths. If I want to express delta phi is just k multiplied by delta d. Okay? The phase is unit to the wave number multiplied by delta d. So it's k is equal to 2 pi over lambda multiplied by this delta d, pi r minus 2r. Okay, so we have both of them and we can work with any of them. Great. So R minimum, this one delta phi, here they told us that let me read it again. There is interference. What is the rejoining results in interference? What is the smallest R that result in an intensity minimum? Minimum intensity, which means that you need to have a destructive, which means you have this one, 2n plus 1 pi. What is the minimum of delta phi? Is 1n equal to 0, so we'll have pi. Okay, the minimum of the phase will be pi, and it will correspond to the minimum of r. So delta phi is equal to pi. This will lead us to pi is equal to this formula here, 2 pi over lambda pi minus 2, and I take r as a factor. Okay, and since we want r, I write it in red. So it's easy, pi and pi simplifies. I will have lambda over 2 and pi minus 2. Okay, So R is equal to 40 centimeter. If I let lambda in centimeter, R will be in centimeter. The other, they are just numbers. 2 pi minus 2 and equal to 17.5 centimeter. Okay, so 40 here, lambda is given in the text. I kept it in centimeter because I have just lambda and R here, both of them distances. If I have centimeter here, R will be in centimeter, no problem. Is it clear here? Is it clear?
دكتور.
نعم تفضل.
Sorry, can you repeat briefly how we get by R minus 2R?
Yes. So we have starting from here. One will take this path until here, and the blue one will take the path until here. It's the same, right? It's the same. The red one will continue here. The second one, the blue one, will go on the top. Okay? And then the blue one continue here, the red will continue here. So here they will cancel, they have the same distance. Here we have the same distance. So the difference of distance will come just from the half circle. Half circle is a circle is 2 pi r. This is a circle. Half of a circle is just pi multiplied by r. Okay, and the distance here, this one is r and this one is r, so it's twice r. This one is the diameter, which is twice r. So this is the distance. The difference between the two distances from here to here is this one. Do you agree? Is it clear?
Yes. Yeah, clear.
Okay. So this is the difference of distance, delta d. Here, I'm working with delta phi. I just need to multiply by k. From delta d to delta phi, just multiply by k. Okay? Everything is clear for everyone? Okay, I consider that it's clear. If you have any question, I can take your questions later also. No problem. So here, number 2, this one is number 3. Okay. So in this one, another chapter here, we have 3 points. 3 points charges are placed as shown in figure 2. The magnitude of Q1 is 5 microcoulomb. So this one is known, but its sign is not known. The sign here is not known. The charge Q2 is not known, while the Q3 here is plus 7. So I can put here plus. So this one is known. This one is not known. This one, only the sign is not known. The force F, this one in red, on Q3 is in negative x direction. So the direction is here. Calculate the magnitude of Q2 and the force F respectively. Great. So here, in order to have a force in this direction, this one needs to be like this, a force in this direction, and this one needs to be in this direction. All right? If you try the other, so this one should be attractive, this one should be repulsive. This one attractive, this one is repulsive. If you try to change any of these vectors, like down or to this direction, you will see that the sum of the two vectors cannot go to the left. So this is the only configuration. The only configuration is like this. So this one is positive. This one should be negative because they are attractive. This one is they are repulsive, so they should have the same sign. This one plus should have also plus here. So here we got the signs. So Q1 is negative. Great. Now the angle here, if I call it theta 1, and the angle here, if I call it theta 2, this one is equal to this one. And the second, probably I put it in blue, it's better, blue, is equal to this one. This is just math. Okay? The two angles are like this. So here I can use the angle θ2, here I can use the angle θ1. Great. So the force here, F, it has only a component along this direction, which means the component along the y direction is 0. So this is, oh, sorry. So the y direction is this one. So the component along the y directions should be 0. Great. I will get this component. So I have this one, this force. I need to project it along y direction. It will give me this. So here I have cosine. So here it should be the sine θ2. So it is F2, 3 multiplied by sine θ2. Okay, and the force between 2 and 3, we know it is, I can change it here, it is, I will work with the amplitudes, Q2, Q3, K over the distance 0.03 square. Okay, so the distance here is in centimeter. It's very important. So I put it here 0.03 square. I will remind you the force is equal to K, Q1, Q2 over the distance square. This is the amplitude. And here I will work only with the absolute value because I want just the amplitude. Okay, great. Now, this one, the second force here, when I project it along Y, I should have the sign minus because it's pointing down. It will point out down. Okay, so it will be K, Q1 multiplied by Q3 over the distance, which is 0.04 square. And here it's also sine of θ2. And all this amplitude is equal to 0. Because as you see, F has an amplitude only along the x direction. So this one, which is the amplitude along the y direction, is 0. Great. Now we need to define sine θ1 and sine θ2. I will use the triangle here. In this triangle, the sine function should be equal to 3 over 5. المقابل على الوتر 3 over 5. I can keep it in centimeter because it simplifies, no problem. And sine θ2 نفس الشيء. Sine is المقابل على الوتر. So 4, sorry, الوتر هون 5. So 4 over 5. Okay, so here we have these numbers here. Sine θ2 and sine θ, sorry, here you should have told me θ2, here's θ1 here. θ1. Great. Okay, let me go here. You can stop me at any moment, okay? If you have any question, you can stop me. So here I will have K as a factor, Q3 as a factor. I will have just inside Q2 multiplied by 4 over 5 minus Q1 in absolute value, of course, over 0.04 square, and here the sine is equal to 3 over 5. I have a product which is equal to 0. All this product is equal to 0. So only this one is equal to 0. Okay. And from here, I can deduce the value of Q. We can find the value of Q2. Yes, Q2 is unknown. So I will have Q2 is equal to Q1 multiplied by, so I put this one 3 over 5, 3 I put over 4, 0, 0, 3, 0, 0, 5 square. It should be something like this. Okay. This is just math. You can do it by yourself. So this one is equal to 0, and you need to express Q2 as a function of the remaining. It can be something like this. You can write it like something like this. So numerical application, Q2 will give us 2.109 10 minus 6 coulomb. You need to be careful. You have here microcoulomb. So when you work, be careful about the units, microcoulomb. Okay, is it clear so far? Is there any question so far? Okay, let me go faster if there's no question. The second relation that we can extract from this one is F along X, which will be in the same way K, Q2, Q3 over the distance square multiplied by, instead of sine, it will be cosine. So here we are projecting here. Okay, so here I need always to keep the absolute value and I should not make a mistake. Be careful about the sign here. Since I'm working with the amplitude, I'm taking the absolute value. Okay, because I'm working with amplitudes, with distances. Both of them are pointing in the same direction. So here I can put plus also K, Q1, Q3 over 0.05 square cosine theta 1. Okay, great. So since you have the sine, you can have also the cosine. Cosine by definition is 1 minus 3 over 5 square, because it's 1 minus sine theta 1 square. So this is the reminder. Cosine theta 2, 1 minus 4 over 5 square. So you can get cosine theta 1 and theta 2 and replace. After that, you just replace. And if you replace, at the end, you will get the answer number 1. I will not do the calculation here because it is straightforward and it's just numerical application. Is there any question? هل في سؤال؟ هل في استفسار؟ So this problem was taken from an old exam. Okay. So I hope I think that there is no question. Do you find that I'm going fast?
No, it's good.
Yeah, I think it's okay.
Okay, great. Thank you. Okay, so now problem number 4. In problem number 4, so we will go to thermodynamics and we look at engines. We have an ideal heat engine which absorbs heat from a reservoir at 5 to 7 degrees and rejects heat to reservoir at 127 degrees. So be careful. In thermodynamics, usually we always work with, most of the time we need to work with Kelvin. So here they are given in degree. So keep it in mind. What is the power produced by the engine if the rate at which heat is absorbed is 1500 watt or 1500 watt? Okay, great. So here we have an engine, a heat engine, which absorbs from a reservoir. So we have a heat engine. We have here, let's say, a reservoir, and it is absorbing. So it is absorbing heat. Okay. It absorbs heat, and this one is at 5 to 7 degrees. Okay. And it rejects this to another reservoir. This one is heat reservoir. Okay, it is heat reservoir, and it is at 127 degrees. Great. We know from our chapter that QL, so L is the low temperature, or the cold for this one, which is given to the cold one. QL over TL, L for low, is equal to QH, hot, over TH. For heat engines, we have this relation for heat engines. Great. Here, we are not working with heat. We are working, here they give us a rate at which the heat is absorbed. So it's not exactly QH, it's QH, the rate, I don't know, probably can put it P is equal to QH over the time. It will give you the rate at which heat is absorbed. So here pH, I can write also PL as QL over T. T is the time. Okay, it's the total time needed to absorb this heat, or to reject this one. Great. So if I divide here over T and here over T, the equality will remain the same. So 1 will give us QL over T is equal to QH over T. So you see here T and T here, we divide it over the same number, so the equality does not change. Great. We want QL over T. What we want? QL over T, it will be equal to QH over T multiplied by TL over TH. Okay, so now QH over T, QH is not given. QH is not given, but QH over T is given, which is 1,500 watt. So this one, the first one is 1,500 multiplied by TL. TL is 127 over 527. Is this correct? Is this correct? Is there any mistake?
No, it's affected to Celsius.
Absolutely. So you need to work in Kelvin. You should not say degree simplifies with degree. So you need to work with Kelvin. You do this. So this is what is required. It is here, they called it the rate at which heat is absorbed. At which the power produced by the engine. So this one, you get 7,500 watt. Okay. Actually, here it's not exactly this. This one is the rate at which energy is released to this one. Okay, it's the rate at which energy is released to this one. So we are having a rate of 1,500 watt injecting in the system and releasing 750. This will give us 750. So the work which is extracted here, the work which is W, it is 750 watt. So this one here. Okay. So you see, it's the same number. So it might be a little bit confusing, but since they want the power produced, the power which is produced, it is here. Here it's what is released to the reservoir. What is produced is here. It's W. Okay, is it clear? Any question? Okay. Let's suppose there is no question. I will go to the next problem. So, as you see, I chose problems which gives you, like, from each chapter I choose one or at most two problems. Okay, here it's not an exam problem, but it's a book problem, and most of the time we take exams from the book. And I chose this one specifically because it has all the details on the chapter, or let's say most of the details on the chapter. Okay, it's a little bit long, but hopefully you can memorize a lot of things in this one. In this figure shows a cycle undergone by 1 mole of an ideal monoatomic gas. So it is monoatomic. This is important. The temperatures are T1. Here it's 300 Kelvin, 600 Kelvin, and here 455 Kelvin. What are the for 1, 2, from 1 to 2? What are the heat Q, the change in internal energy, and the work? Okay, the change in the internal energy and the work. Great. So there are some relations that you need to keep in mind. First of all, we have delta E. Delta E is equal to N CV delta T. Okay, N CV delta T. When can we use this relation? It's very important to know when you can use a relation. This one, you can use it all the time. Okay, very important. Delta E equal to NCV delta T. Its state function, it depends only on the change of delta T. Great. Now Q. We can find two relations. Okay, we can find NCV delta T. We can find NCP delta T. So where can we use this one?
With a constant volume.
Great.
Constant
volume, and here constant pressure. So you see this one always for delta E. This one, which looks like exactly the same, you can use it only for constant volume. If you have constant pressure, you need to use the second one, NCP, not CV, CP delta T. Okay? And for the work, W. So what should we use for W?
For which part?
In general, the relation is
Also same.
P delta V.
Sorry?
The general one, P delta V, or we can the other thing depend on the path. Which
Okay.
path?
Before choosing the path, let's do this one. We say this relation is always valid. Delta E is equal to Q minus W, right? So if you have this, and this, you can get everything. Okay? Great. I will come back to W later. Let me write on the half here. So for the first one here, from 1 to 2, they require the heat and delta E and the change in and the work. I will start with probably delta E. NCV delta T, and we have 1 mole CV. What is CV? Since it is monoatomic, this is 3/2R, okay? Multiplied by delta T. Delta T is the final minus the initial. The final here is 2, which is 600, minus the initial 300. So it's 600 minus 300. Okay? And if I do this, it will give me 3.74 10 to power 3 joule, or 374 kilojoule delta E. Here, which kind? What is the name of this process here?
Isobaric.
Sorry, again?
Isobaric or curve.
Okay. Yes. So here we have a constant volume, right? You see here, if I go down, the volume is always the same. Okay. Since we have a constant volume, so Q is equal to N CV delta T. And this, since it's the same, it will give me the same thing. 374 10 to the power 3 joule. For W, I can say that it's delta E. From here, it's Q minus delta E. I can say it's Q minus delta E, which gives 0. Okay. Or from the beginning, we know that since the volume is not changing, so there is no work. W is equal to 0. Okay. Great. So this one is for the first process. Now from 2 to 3. 2 to 3. From 2 to 3, the process is adiabatic. Okay? An adiabatic process is known for Q equal to 0. So this is the most important information. Q is equal to 0. For an isochore, it's W equal to 0. I can start directly from this one. For an adiabatic, I can start with this one. Q equal to 0. Then, if I want delta E, it's N CV delta T, which is 1, 3 over 2R, and delta T is given. We have 455 minus 600. The value of R is given. It is in your formula sheet. Okay, so you can use it. Let me check here. So the value here, minus 181 10 to the power 3 joule, which is minus 1.81 kilojoule. Okay, and it is negative here. Okay, it is negative because delta T is the final minus the initial, and the final temperature is smaller. Great. Now we go to the last process from 3 to 1. They require the same thing. 3 to 1, they want the same thing. Okay. Three to 1, how do we call this process? How do we call this process? The words are important.
Isobaric.
Isobaric, absolutely, thank you. So since it's isobaric, so the pressure here is the same, right? Let's say delta E is equal to NCV delta T. We said that this one works all the time. So I can start, for example, with this one is 1 mole 3 over 2 R multiplied by delta T, which is the final temperature is 300 minus 450. Is it 455? Okay, and if I do this, let me check here. It's minus 1.81 again, if I am not wrong here. Great. Oh, sorry, we did not get W here. Here, I will write it in red. Sorry, here. Q equal to 0. So delta E is equal to Q minus W, which means 0 minus W is equal to. Okay. So from here, you deduce W minus delta E, and it's equal to plus 181 kilojoule. So this one for the second part here. I will come back here. Delta E, I have this. Let me check if the numbers are correct. Oh, sorry, one moment. 455, no. I think I don't have the number for this one. Okay, Okay, I don't have the, sorry, this one I did not bring the number for this one. But the most important is this one. Okay, you do it like this. 1 multiplied by 3 over 2 are 300 minus 455. Then we need Q. Oh, sorry. Q here is equal to what? It's isobaric. Since it is isobaric, I need to use this one. It's N CP delta T. Okay? And N is 1 mole. CP, I think it should be in your formula sheet, it should be CV plus R, which means 5 over 2 R. And delta T is 300 minus 455. Again. You do the application, numerical application here. It's easy. And the third one, W, it's just delta E or Q, sorry, it's Q minus delta E. It's Q minus delta E. So this one minus this one. Okay, I don't have, sorry, I don't know why my numbers are not here. But anyway, so I wanted like to explain for you again this chapter because it's very, very important. Do you have any question? This is very important. Delta E all the time. NCV delta Q is NCV delta T or NCP delta T. Okay, this one constant pressure, this one constant volume. And here, with the third relation, you can get any value for W, Q, and delta. Any question? Okay. So I suppose it's clear. And I will go to problem number 6. Okay. The volume of an ideal gas, so it's an ideal gas, is adiabatically. So this word is very important. Ideal gas and adiabatically reduce it from 200. So if I make a graph, we have some point here, and if we are here, if we go like this, so if we go in this way, so we have some volume here, and here the volume becomes smaller. Another volume here at this point. So P, this one is adiabatic, so Q is equal to 0. The initial pressure and temperature are 1 atmosphere and 300 Kelvin. The final pressure is 4 atmosphere. Is the gas monoatomic, diatomic, or polyatomic? Okay, so we need to know if it is poly, mono, or diatomic. Great. So what's the relation that we have when we have a transformation like this? For an ideal gas, we have PV is equal to nRT. This one is always valid. PV equal to nRT. This one for an ideal gas. For a process, if we have now a process which is adiabatic, I can state that PV to power gamma is constant. P multiplied by V to power gamma is constant, which means the initial value PVI gamma is equal to the final to power gamma. So adiabatic, you need to keep this in mind. I have this relation which is valid. This one that I should use. So they want from me the final pressure. They gave me what they gave me, atmosphere. Yes. Sorry. They gave me the final pressure. They gave me the initial and final pressure and volume. What they did not give me is gamma. Gamma is unknown. So I need to get what is gamma. Great. So I will write Pi over P final is equal to V final over V initial all over gamma, exponent gamma, sorry. I will take the logarithm of this one. Let me do it here. So my aim, my objective is to get gamma. So log Pi over Pf is equal to, and the properties of the log, that the log of this one is equal to gamma log of V final over V initial. Okay, here I can get gamma. So it's log Pi over Pf over log Vf over Vi. I need to be careful. Here, I do not need to make a transformation in the units. Since it's a ratio here, P over P, I can keep it in atmosphere. So the P final is 4. And initial is 1. Here, it's log. The same thing. I should not transfer it to meter cube. I can keep it in liter. So it is reduced from 200 to 74. So the final is 74. And here it's 200. Okay, great. When I do the calculation, I obtain gamma is equal to 1.4. Okay, gamma is equal to 1.4. 1.4, if I look at the fractions, 1.4 is around 7 over 5. Okay, 7 over 5. And gamma, I will remind you, it's CV over CP. CV over CP or CP over, I think it's, no, CP over CP, sorry. It's more than, larger than 1. If you look, the value that you have of CP and CV for monoatomic, diatomic, or polyatomic, you will find that you have a ratio which is 7 over 5, which is the closest to 1.4, which means, so gamma is equal to 7 over 5. This means that the gas is diatomic. Okay, is it clear?
Yes, good.
Okay, great. So be careful, keep this in mind, this relation. Adiabatic, PIVI, exponent gamma is the constant, so the initial is equal to the final, like this. Great. Now, there is another question. How many moles are in the gas? Okay, so to answer this question, okay, I can use, yeah, first of all, I need to get T final. Sorry, there's one question. What is the final temperature? V. What is the final temperature? The final temperature. How can I get the final temperature? I said that this one is valid all the time. This one is valid all the time. I don't have the number of moles. Can I use it? Yes. How can I do that? I can say that Pi, Vi, N, R, Ti. So this is initial. I'll divide it over P final, V final, here, N, R, T final. And I simplify. N will simplify, R will simplify. So this will give me P initial, V initial over P final, V final is equal to T initial over T final. And from here you can deduce T final easily. It's just math. It's the T initial and P V final over P initial V initial. I think, is it correct? P final, P final. No, sorry, initial here. and here is final. Okay, so I have this, I have everything here, I have pressure over pressure, volume over volume. I keep the same units, I do not need to change atmosphere or liter, and at the end I will get the temperature equal to 446 Kelvin, the temperature in Kelvin. And the final one, N, they want from me N. I can always use this relation. It's PV over RT. I can use the initial or the final. I have all the numbers. So I can use initial here, TI. I can use the initial. And numerical application, I will not do it here since it takes time. It's 3.10 moles. Okay. So here you have all the aspects on this kind of questions. How to use the relation when you have adiabatic transformation. You should not forget that you have an ideal gas, so PV equal to nRT all the time. That if you have the value of gamma, you can deduce which kind of gas that you have. Is it atomic, diatomic, or polyatomic? Gamma, by definition, you have it Cp over Cv. It's in your formula sheet. And the final temperature, you can use always this one, and so on. So is there any question on this regard?
Doctor, the pressure ratio should be down, not up.
Sorry?
The T final should equal to T initial, P final, V final. Not should be the opposite.
Here, you mean here?
Yes, yes, doctor, you reverse it.
Yes.
One moment. Absolutely, yes. So what I wrote at the beginning was right? Okay, up here. Yes, absolutely. So it's just you go from here to here. So TI, so here you'll have up PI, VI here, and P final, V final. Yes, thank you very much for this reminder. Any other question? Okay, great. So let's go to the next problem. We are running a little bit of time. So I think number 7. Yes. This one is very simple, very short, but it's very important. A steel rod is 3 centimeter in diameter and 25 centimeter at 25 degrees. Sorry. A brass ring has an interior diameter of 2992 centimeter at 25 degree. At what temperature will the ring just slide onto the rod? Okay, great. So a steel rod is 3 centimeter diameter. So we have a rod like this, and we have a ring. On top of it, let's say we have a ring like this. Okay, but put in mind that the radius of the ring is smaller than this one. Then the diameter of the ring is smaller than the diameter of the rod. So this ring cannot slide. It cannot slide. The two here are from 2 different materials. This one is steel. This one is brass. Okay, the ring is brass. This one is steel. So there are 2 materials. Okay, 2 different materials. When this is at 25 degrees. Now, if we increase the temperature, the distances of the characteristic distance of each material, of each object here will change, and they will change differently. Okay, for steel and brass. So at some moment, the diameter of the brass will be exactly equal to the diameter of the steel. Okay, the diameter of the brass will be exactly the same as the steel and so it will slide. It can slide. Okay. Great. Let me just. Okay. So all the distances, all the characteristic distances of the object will increase. When you increase the temperature, all the distances will increase. So I will work with the diameter. Let's say the diameter of the steel. It will be equal to the diameter of the steel at the beginning plus alpha of the steel delta ds0 multiplied by delta t. Why I can use this one? Remember, I will put it here. The general formula, what does it say? Any length, it will become delta L alpha L delta T. So delta T is here. The length I'm looking at is the diameter. Alpha is here, and this one is, if I take this one to the left, I will have delta D or delta L. Okay. So I am using this formula, this general formula. Okay. Now the same thing for the ring. So for the ring or the brass, I will write it in green. B is equal to D B0. This one is the brass, is equal to alpha B, which is different for steel and brass, have different coefficient alpha B0, and here we have delta T. Delta T will be the same because they were at 25, and they will increase the temperature the same way. So good. We need to get delta T. Okay, so we want to have delta T. This one, yes. First of all, this relation we need to search delta T at when ds is equal to dB. Why I'm doing this? So this one, the diameter is here, is equal to this diameter, because I'm looking at the moment the brass here or the ring will slide. So it will slide at the moment they will have the same diameter. So I remind you that the ring has a smaller diameter. It will increase until the moment it will have the same diameter, and then it will slide. That's why I will solve this one. So ds is equal to dB, and I will find delta T. So this one equal to this one, so this one minus this one, 0. Here ds 0 minus dB 0 plus alpha s ds 0 minus alpha b dB 0, all multiplied by delta T. Okay, so I just did 1 minus 2. Equation 1 minus equation 2, and I put in mind that ds is equal to dB. Okay, so I find the delta T. I put this one on the left and divide over this one. It's dB 0 minus ds 0 over alpha s ds 0 minus alpha b dB 0. Okay. Here you need to be very careful in the numerical application, because everything is very small, so you need to keep everything. Here this distance is in centimeter, the d here is in centimeter. I can keep it in centimeter, no problem. 3 minus 2.992 over alpha is 19, 10 minus 6, here 2992 minus probably B. Okay, so minus 3. I will so this one is 219, this one is 3, and this one, okay, this one is it should be 3 here. Okay, for steel it is 3. said it is 3 centimeter. Yeah, for alpha usually it should be given. Alpha should be given in the formula sheet or in the exam. And here 11.10 minus 6, and here sorry, here it's 11 and here it's 19, and minus 6 multiplied by 2.99. So it's just numerical application, and here we will find delta T, which is 335 degree. Okay. Since it is a difference of temperature, it doesn't mind here if you say Kelvin or degree. A difference is always the same, but the temperature is not the same, but the difference, no problem. Okay, so this is it. We have delta T. So we need to add it to 25 in order to have the temperature. So the total temperature, T final, is equal to T initial plus 335. It should be 360. Yeah. Any question? Any question? No? Okay, great. Okay. Let me check. Okay. We are running out of time. Let me see. I will choose a problem. Okay. Yes. Here, in this problem, I have a function. So here it's something which is oscillating. Y x of t, x and t, 15 centimeter cosine pi x minus 15 pi t, with x in meters and t in seconds, describes a wave on a taut string. The taut string, so it's taut. What is the transverse speed for a point on the string at an instant when that point has a displacement y is equal to 12 centimeters? Okay, so they want the displacement. So we have this. So each point on the string will oscillate in this direction. It will oscillate. They want the velocity in this direction that we call u. Okay, but they did not specify the time. This which makes this problem a little bit difficult. Let's see how to solve it. First of all, we need to express u, the speed of a point. Let's say it's this point, this red point, which is oscillating on this. So it's, be careful. This one is different from the velocity of the speed of the wave. Sorry, the wave will propagate this way, but the particle travels or oscillates this way. So it's different from v. This is u. Great. So u by definition is the derivative of dy over dt. And if we derivate this, so I have 0. Sorry, yeah, everything is in centimeters, so I can keep it in like this. The derivative of this one, I have 15. The derivative of cosine will give me minus, and the derivative of the time here will give me 15 pi and t with the sign minus, another sign minus, so I will have plus. Okay, sorry, why I don't know why I wrote t here. There's no t. It's 15 pi. Okay, here sine of the same thing, cosine will become sine pi x minus 15 pi multiplied by the time. Okay, great. So u is equal to 225 pi cosine of this one, this guy here. Great. We have u and we have the function y here. The problem is that they did not give us the time. They just told us it's at a time where the displacement y is equal to 12. So I need to replace here y by 12 and solve this one, but it's not easy. It's not easy because you have x and you have the time, and you have a problem of the sign. Always, are you going up? Are you going down? So it's not easy. The best way to solve it is to remember that we have this relation. I put it in red. Cosine of anything square plus sine of anything square, the same angle, is equal to 1. So I will use this relation. I have here sine. I will express it. So I will say that sine of pi x minus 15 pi multiplied by the time is equal to u over 225 pi. Okay, and cosine pi x minus 15 pi t, I will deduce it from here, from this formula here. It is y over 15. So this one is number 1, this one is number 2. Since I have my cosine and my sine, I will use the relation here. It will give me this one square plus this one square. It will give me 1. It will give me u over 225 pi square plus y over 15 square. Okay, so why I did this? Why? I used this relation to eliminate the time and the position at the same time. Okay, here since sine square cosine square gives me 1, I eliminated the time. Okay, so here I'm searching the transverse speed, this one, the speed. So I'm searching for u. So it's easy. So u is equal, I put this one, it's 1 minus y over 15 square. I need to take the square root like this and multiply here by 225 divided by 5. So this is just math. Okay, y is given here. Y they said is 12 centimeter at a position 12 centimeter. So u is equal to 225 pi multiplied by 1 minus 12 over 15 square. Okay, and this will give us 424 centimeter per second, because I kept it in centimeter. Okay, and 424 meter per second. Any question? Are you still there? I hope.
Yes.
Yes.
How
Yes.
do you take the U on the left side?
You mean here? Here?
Yes, here.
Here I did this. I take equation number 1 square plus equation number 2 square. What does it give? On the left side, it gives me sine square plus cosine square. صح? This is on the left side. On the right side, it will give me this one square, u over 225 pi square plus y over 15 square. But square, these two squares gives me 1. The sum is giving me 1. I did it on purpose to have 1. Okay, and I get this formula here. So the advantage of this formula is that it does not have time anymore. It doesn't have time anymore. Okay.
Yes, clear.
Okay. And also it does not have x. It does not have x because here x is not given. So probably if you can try to replace here y by 12 and try to solve this one, you need to cheat a little. You need to cheat and say, since this is valid for any x, I will take x equal to 0 and solve it. It is possible to do that, but it's not like it will lead you to the answer. It will lead you to the answer. It will be a little bit more difficult. Yeah, but it's not like very clean. But if you can do it in the exam, no problem. But here it's the simplest way, the simplest and the easiest. Okay, if there is no question on this problem, I can move to the last one probably. Let me see what I can here. We have, yes, probably this one is. Okay. So this one. Here, a copper rod has a length of 60 centimeters. So we have 60 centimeters. One end is maintained at 80 degrees. So here on the left, 80 degrees, and the other end is at 20 degrees. What is the temperature of the rod at a point which is 20 centimeters from the hot end? 20 centimeters from the hot end. So here the formula is very simple and well known. It is K multiplied by A multiplied by let's say T x minus T. So so this one final minus this one is over the distance L. Okay, is equal. If I calculate it, this power here at between at here at this point, it will be the same between 2 points. Let's say this one and this one, for example. So here it's K. I will calculate it on between 2 points here. K T minus 20. So I calculated at this point between this one and this one. So this is on the left. I need to write the distance 40 centimeters here. Okay, and if I calculate it between this point and this point, it will be here, and I will write L equal to 20 centimeters. Okay, I can work in centimeter, but let's put in international unit just to remind you. K will simplify. The area on the left is equal to the area on the right. So I need to find T. X here is 80 because I chose between the 80 and this point. 80 and this point. So here it is. I replace it by 80. This is very easy to solve. So I have 80 minus T 0.4 is equal to 0.2 T minus 20. I'm sure that all of you can solve this. I take 0.4 to the other side. So 0.4 multiplied by 80 will give us 4 for 8, 32. And here 0.6 multiplied by t, and this one will give me 4 minus 4, give me plus 4 here. So t should be equal to 36 over 0.6, and this should be equal 660. So 60 Kelvin, right? Is it right? Everything is correct? Are you following? Yes?
The area.
Yes?
I think that is equal.
Sorry?
Anyway, the area. What
Yeah,
do you mean by area?
the area is they are equal. Since they are equal, I simplify.
How they are equal?
It's the same rod. It's the same rod. Here it is one rod, so it has the same area. Here.
I mean the total area.
It's the cross section. The cross. Oh, sorry. Oh, be careful. Yeah. Thank you for pointing out this. It's not this area. Neither this. No, it is the cross section, which means the rod is like this. Okay, so it's this area. So it is the cross section area. It is the cross section area. So be careful. Thank you for pointing out this.
Yeah, welcome.
Okay, so here, no one told me this mistake here. Here, is it a temperature or difference temperature? It's a temperature, right? I put it in Kelvin, so it is correct. Is it true?
No, because it's Celsius.
It's Celsius, yes. Because here the temperatures I was considering here, they were in Celsius. So 20 degree here Celsius. So the difference of temperature I need to have also this one also is in Celsius. Okay. So the temperature is from the beginning in Celsius. All what I do here at the end, it's in Celsius. Okay. Any question? No? Okay. A final problem probably. Are you tired? Let's finish with this one. A final problem, just to have a flavor of different subjects. How much mass of aluminum initially at 150 degree must be added to 500 grams of water in a container initially at 20 degree to make the final equilibrium temperature 50 degree? Okay. So here we neglect the heat capacity of the container, and the specific heat of aluminum is 0.215 calorie per gram per degree Celsius, and for water is 1. Great. This one is very simple. It's straightforward. So there will be an exchange of heat. So we have a container. We neglect the mass and we neglect the capacity of the container. Initially, it has some water, and the water is at 20 degrees. We put inside some aluminum, a mass of aluminum, let's say, and this aluminum was at 150 degrees Celsius. So what happens is that there will be exchange of heat. There will be exchange of heat between water and the aluminum. The heat released by this one will be the heat absorbed by the water. So the heat released, here we have just two elements, so we can write directly an equality. The mass of water multiplied by the capacity of water multiplied by delta T final minus T initial. Okay, So here, this one will give you the heat which is obtained by water, or yes, is equal to M of this one aluminum, IL, and C of aluminum, and here T initial minus T final. Okay? Be careful here, I exchanged the initial minus final, because here I'm expressing the heat which is released by this one. Okay? So I need to write to change this one to make it positive. So here 500 grams multiplied by 1 multiplied by 50 minus 20. The final temperature is 50, is equal, the mass of aluminum is, what is it? 150, I think. No, 0.215 multiplied by 150 minus 50. So the temperature initial is 150 minus the final is equal to this. And here, sorry, M. Okay, so here is the aluminum capacity, it's this one. I have just one variable here. Some math will give me the value of M aluminum, 700 grams.